I found a system for it. Thank you. এটা কত কিছু করবো?
আমি জোগাড় করেছি কাছে যায় একটা দোকান থেকে।
থ্যাংক ইউ।
This is the last.
Okay.
Should we? Because समस्या नहीं बनते हैं.
Yeah. Yeah, the highest of the VC, good color.
I work all of this stuff. Of course. I have really enjoyed your talk. And you worked on the against good guidance to it, so.
So it's all, remember.
I was not hearing, but I could read it better. So we may have to. Yes, Jimmy.
This is not working again.
Again?
No, just switch off. It is a problem that Jeffrey is.
Connected. So what can we face that?
No, it was a loose connection on the top. You were talking better on the.
Like already means something, doesn't really last. Then the field, the care of first. I'm supposed to ask. I say things. I know, but I can't. There's no chance. More than.
Did anyone reply?
Did you reply?
No.
So. All right, so I hope you had a good snack. So first of all, my apologies for the speaker for the next session because I won't be able to do a good justice of giving you a good introduction like JD does. But okay, so let me introduce Professor Stephen Mick from University of East Anglia. So he is a pioneer in excited state dynamics in quantum space. So he does spectroscopy, ultrafast spectroscopy in molecular system as well as in protein space system. So we look forward to your talk today. And it was a very short introduction, but I hope his work will speak for himself. So okay, without further ado, this go ahead.
No, we will see. You be the judge of that. Okay, so thanks to JD for putting this together at short notice. I've really enjoyed it. It's been fascinating, and it's a chance to visit GIFR, which has become a must-visit place in the past 15 years or so, at least for molecular scientists. It's something that's been growing here, and so it's really exciting to be here. And I hope I get a chance to look around all that. Okay, this talk is as titled. Ultra-fast photochemical mechanism of fluorescent proteins. It's the classic fluorescent protein, green fluorescent protein shown here. I guess everybody's familiar with this. It's the premier, arguably the premier tool in bioimaging. You can label a protein specifically with this protein, and then you can follow it throughout its life with fluorescence microscopy because this molecule is highly fluorescent in the visible region. If it was only fluorescent, then this would be a very short talk because it wouldn't tell us very much. But actually, this molecule does a surprising number of photochemical reactions. And I will touch on a couple of those. I won't touch on all of them. And so for me, this is kind of a little nano laboratory here where we can tune the chemical reactivity by messing around the mutations in the protein. So that's what I'll be talking about. From the point of view of motivation, it turns out that some of these chemical reactions are fortunately very useful in super resolution bioimaging, and that's good for talking to the funding agencies, as has already been mentioned. But that's not what really drives my interest. Okay, so this is our chromophore. It's formed in a reaction between three amino acid residues. It's a reaction which happens in the dark. There's a cyclization reaction, dehydration reaction, and then an oxidation, which gives us a extended conjugation over here. So then this becomes absorbing and fluorescent in the visible region of the spectrum. The biological function of this is not absolutely clear. In the jellyfish, where it was originally discovered, it's part of the signaling apparatus, but it's also been discovered in a whole number of other marine organisms, very similar proteins, and its function there is not clear, possibly photoprotection, but it's obvious that the protein cares about it because it's wrapped this beta cam, so it's a beta sheet, all around, trapping the chromophore right. So this is the guy that we're going to be studying photochemically. I'm going to be studying it with ultrafast spectroscopy because I don't know how to do anything else, but I'm sure other methods are available. We're going to be using three tools. One of them is time-resolved fluorescence. Time-resolved fluorescence is great because it does one specific job really well. It shows you the decay of the initial excited state. Now, when we put a molecule into the excited state, then it immediately starts to fluoresce. And if we time-resolve that fluorescence, then we can see the decay of that Frank complement excited state. So in a sense, this specifically looks at the initial reactions in photochemical reaction. The downside is that's all it can do, whereas transient absorption has the advantage and the disadvantage that it looks at everything is absorbed. So let's see the reactant, the product, and any intermediates. So you get this quite complex overlapping spectrum of bleaches and transient absorption. Of course, if we can combine these two, then we can use this at least to resolve out the reactive part of that mechanism. So these work really well together in general in photochemistry, and in most photochemical problems, that may be all that you, or at least that's a good starting point to understand excited state dynamics. When we move to photobiology, then doing transient absorption in the infrared region of the spectrum, so-called time-resolved infrared spectroscopy, is a very powerful tool. Because, of course, it also observes the chromophore, in this case through the vibrations. So this is an example I'll come back to. The blue labeled bands here are associated with the chromophore. And we know that, and we can see that from model systems. Everything else here is a contribution from the protein. So by doing, and you won't see that in transient absorption, because we're now back in the ground state. That's what photobiology does, is the absorber does a chemical reaction, and then that chemical reaction does something to the protein, and that's where the function of the protein starts to appear. So time-resolved infrared gives us some insight into the structural changes associated with the function. So putting these all together is a fairly powerful tool. We do the data analysis with a tool which is not terribly powerful, to be honest, but it's widely used. We apply global analysis, which assumes discrete states connected by unimolecular steps. Most reactions, certainly most reactions in biology, probably don't go by that mechanism. So all we can extract from this really is not kinetics, not mechanism, but we can see one state evolving into another and how long it takes. Actually getting mechanistic data is much more difficult. Okay, so let's start off with the chromophore alone and in solution. Given that its name is the green fluorescent protein chromophore, it's disappointingly not fluorescent, given about 10 to the minus 4. And there's a corresponding fluorescence upconversion, so the lifetime is about 200 femtoseconds in a fluid solution, also methanol, etc. So those two facts match up. And this, if you ask any photochemist, that's not really very surprising because you would expect there to be some kind of excited state isomerization reaction about that double bond. There are many systems in which that is done. But what we do know is that we can freeze this down, and once we get to an extremely viscous liquid, or then into the glass phase, we enter the glass phase about here, then it does become porous. So there's some internal motion in this, indeed some kind of isomerization reaction, which is driving this radiation. The excited state dynamics of this chromophore have been studied in great detail, actually by many computational chemistry groups. This is one of the more recent and one of the higher level calculations from the Martinez group. I suspect this is partly because the molecule is intrinsically interesting, and partly because it's got few enough high electrons for these kind of calculations to be not too expensive. So this has been a very well studied system. Ground state, planar, put it into the excited state, this potential energy surface is more or less flat. And then you'll see, this is the isomerization coordinate about both of these bonds. You see a reaction, and then mainly population goes through a conical intersection here, where then 90% of the population goes back this way. They say 30%, but our experiments show 90%, whereas about 10% go this side. So that's this flat potential energy surface suggests kind of a diffusive problem. So we had a look at this just by applying a simple diffusive mechanism for how long does it take to get from here to here. And we find that we can model this quite nicely. So it is indeed a flat potential energy surface. Surprising thing is that if we apply normal hydrodynamics, so just assume that the viscosity is the thing which is controlling this, then we have to have an extremely low volume of rotation, actually much too low for this volume here, which does suggest that maybe there's some kind of more complicated reaction coordinate going on with this molecule. And I'll come back to that later on. Okay, so we've got a molecule which does essentially nothing in solution. Mainly goes back to the ground state, a little bit of isomerization. Put it in a protein, and it can undergo all of these, depending on the protein, can undergo all of these reactions. So I'll be talking excited state proton transfer, common. Excited state isomerization also occurs. It can fluoresce with very high quantum yield, or not. Some proteins don't. It undergoes, so actually all of these, about this region, from the blue up to about here, that's all the same chromophore. The color is being tuned only by the protein environment. That chromophore can undergo a chemical reaction with an adjacent amino acid residue in some cases, which causes an extension of conjugation. So that's a stronger red absorber. And all of these colors up here can be associated with chromophores. Just another, it also undergoes rather efficiently, actually, in some proteins, a photohydration reaction, which if you're at the conference next week, I'll be talking about that. If you're not, you can ask me about it later. That undergoes this photohydration reaction. It's actually driven by an electron transfer reaction, and it undergoes actually a variety of other electron transfer reactions. So this is the same chromophore, all of these reactions being induced by changes in the protein environment. It's the same protein structure, it's the same beta-can structure. Just differences in the precise environment of the chromophore can completely change the excited state reactor. I will only be talking about these two today, so I'm going to kick off by talking about the excited state proton transfer reaction, and then I'll talk about the isomerization reaction, which is in super resolution biology. Again, I'm going to be talking about time-resolved infrared spectroscopy, so it's useful at the outset to see how the spectrum looks of just the chromophore on its own. And the ground state, so these are bleaches, so these are the ground state modes, and they're well assigned. This is a carbonyl, this is basically a CC stretch, shown here, and these are the symmetric and antisymmetric stretches of the phenol. And we've characterized that for the cis and the trans, and also the two different charge forms of this chromophore. So we know what the chromophore infrared spectrum looks like. Okay, so let's look at the excited state proton transfer reaction in the green fluorescent protein. And it turns out the green fluorescent protein, we already know it's highly fluorescent. So if we excite it to this band here, which is the anionic form of the chromophore, so where that proton is missing, has a pKa, the molecule in solution has a pKa of about 7.5, so you can actually get both of them in a protein physiological pH. If you excite this one, then you see this anion spectrum. If you excite the neutral form, where the OH remains, then you also get this spectrum with a little bit of signal down here, which depends upon whether we're looking at OH or H2O or D2O. So this is pretty clearly an excited state proton transfer reaction. Time resolved fluorescence confirms that nicely. This is the decay of the neutral form measured around here. This is the rise time of the emission measured over here. So a classical excited state proton transfer reaction. These were our measurements, but it was characterized much earlier by the Boxer group way back in 1996. So that's a long time. So this has been known for a long time. We extended this by looking at using time-resolved infrared spectroscopy. This is the figure we saw earlier. And the advantage of that is now we know that proton's gone, but now we can use time-resolved infrared to see where did the proton actually go. And when we make the measurements, we can see that we have a product which grows in here on a tens of picoseconds timescale at around about 1720 wave numbers. So every good undergraduate student will tell you that that's probably C double bond O stretch. And if you look in this mess around here, then you can see that there's some bleach which is appearing on the timescale tens of picoseconds. So what we're seeing here is a carboxylate. It's a carboxylic acid transformation. So our proton is going to a carboxylate residue to create carboxylic acid. Structure of these proteins is well known, so we now go to look at the structure, and we can see that the only game in town in terms of accepting that proton is this residue out here. So our proton is actually leaving here when we put this in the excited state to make it into a better protoacid. It's kicking the proton out, and then it's going via a structural water molecule, this serine residue, going to this glutamic acid. So what we have is a proton wire, hundreds of picoseconds in the mutation. But the wire can reform, the protein can repair itself. But there's a price to be paid for that. You can see that the yield of the proton transfer reaction is rather low compared to this one. The scales are different, but this one is smaller, so that quantum yield is really quite low. Kinetics is slow, as I've already said. And the back reaction, however, doesn't really change very much. So apparently, the forward and backward rate determining steps are different for this particular proton wire. Okay, so that's one thing we can do. We can manipulate the excited state dynamics of these, or the dynamics of the excited state proton transfer through mutagenesis. We can do other things. We can short circuit that wire. So if we put a different acceptor, we make the H148D mutation. So we essentially put our carboxylate right in hydrogen bonding distance with that OH group. Then we can get a really fast proton transfer in a couple of 100 femtoseconds, actually about 100 femtoseconds. Then that blue form decays and there's a rise time on the red edge of the emission. So what we're doing there, of course, is we're shortening the distance between the first acceptor, which is actually not the E222, the first acceptor would be the water molecule shown here. We're shortening that distance. We shorten the distance, we reduce the barrier. We're creating what's called a low barrier hydrogen bond. Or there are arguments about the exact definition of what a low barrier hydrogen bond is. So we're shortening that distance and reducing the barrier to the proton transfer reaction. So this proton transfer essentially happens ballistically on a time scale of less than 200 minutes. We haven't time resolved all those protons. Okay, so by playing with this, with the structure of this chromophore around this proton wire, we can have quite a dramatic effect on its behavior. which gives us a lot of chances for other people maybe to simulate the cyclonic cells.
And what's corrugating symbols?
Are these are measured?
Like corrugating fluorescence or,
This is fluorescence, yes.
but you're doing corrugating.
Okay, no, upconversion.
Upconversion.
Sorry, yeah. The time resolution is a bit worse for corrugating in my view, although you do get the whole spectrum.
Yeah.
Which is kind of nice. Yes, so if you really push up conversion, you can get to 50 femtoseconds, or actually 30 femtoseconds if you're tight RG. But we never got those. Okay. So I'm going to leave the excited state proton transfer reactions and start to talk about some more recent stuff that we've been doing on photoisomerization reaction inside proteins, and we're interested in that because this is the main feature of reversibly switchable fluorescent proteins. All of this stuff is in the last couple of years, and a very able postdoc, Anand Fatima, who's been in my group a couple of years now, done a PhD in France, but it's originally obviously from India. Has been doing a really great job. So we're trying to keep her a little longer. So reversibly switchable fluorescent proteins. A different class, these molecules are not always fluorescent, and they're characterized by this behavior here. We start out, let's say the ground state is the cis anion. This is the specific case of a protein called DROPA. If we irradiate that, then mainly it fluoresces with a very high quantum yield, characteristic of the anionic form of the chromophore in the protein. But slowly over time, that converts to form this character here. This is a cis-trans isomerization reaction, and we know that because somebody's measured the structure of the dark and the light irradiated forms. Not somebody, Anderson and co-workers, Stefan Hell's group. So we can see that the isomerization reaction has happened, but we can also see that there's been a proton transfer reaction between these two. We now know, I won't go into the details of it, but we know that the isomerization reaction happens first, and the proton transfer happens in the ground state on a much longer time scale, up to a millisecond. So this is the total overall reaction. It's a photochemical isomerization accompanied by a proton transfer. The key thing about this, and the reason these proteins have excited so much interest, is that you can then repeat this process. So it's a real, like the photochromic system that Dwayne showed earlier, you can just keep going backwards and forwards. It's not perfect, but you can go backwards and forwards 1,000 times. Which is kind of neat, and it has important applications. I won't go through the full details of this in the interest of time, but this is the behavior that underpins super resolution imaging, because either for the photolocalization, single molecule localization measurements, or the so-called stimulated emission depletion measurements, very important to have a really efficient single photo switching. Stimulated emission depletion, of course, it's a great idea, but it's not, but it's a non-linear optical transformation, which requires high energy, so it's not the best thing to apply to a protein. However, if you make the same donut mode and apply it to reversibly switchable fluorescent proteins, then of course you can switch with much lower patterns. And that's why this method, Resolve, as it's now called, but I've forgotten what it stands for. But this method is available to give you at least sub 50 nanometer spatial resolution in an optical microscope image. So it's a really powerful tool. And again, it offers us the chance, photochemists are interested in how the reaction happens in proteins. It offers us the chance to observe real-time reaction dynamics, isomerizations in this case, in protein. Okay, there are 3 different mechanisms for reversibly switchable fluorescent protein. I'm not going to talk about all of them, JD, so don't worry. But it's interesting again that, okay, we have one mechanism here. This one goes cis, trans, proton on, off, thousands of times. But the problem is, as you start to image this, you're always converting it That's good. As you start to image this, you're always converting it back to the off form. And that means your image will fade over time unless you do something else. What we call a positive photo switch is where you start off again with a trans off form, but now in the anionic form. If you irradiate this, then it goes first to this state, anion, goes to the cis anion, but then it forms an equilibrium, pKa type equilibrium, acid-base equilibrium, with the neutral form. Interestingly, this form does not undergo the reverse isomerization. This form just fluoresces, which is what you want in bioimaging. And that fluorescence is steady. If you want to do the conversion, the back reaction, you have to irradiate this guy, and this transforms into that. Precise mechanisms for that are not known, although we've got some data on it. And then the really strange one is this, what's called decoupled. So this you have two separate wavelengths, which have two separate effects on lock switching. Here you have three different wavelengths, and the photochemical reaction here, our off form, is this strange hydrated form of chromophore, which is only formed from the neutral cis form. So these are all cis, actually, there's no isomerization reaction. And that's formed in a photohydration reaction. So we hydrate on that double bond there. And then if we irradiate this, it goes back, but these two are in equilibrium. If we irradiate this one, we just get fluorescence. And that's steady fluorescence. So now we've got three wavelengths. 340 nanometers to affect that transition, 405 nanometers to affect that transition, and 505 nanometers to do that. So this looks like it would be a great tool for some kind of optical read-write optical memory and things like that, except that it happens to be a protein. It's probably not that different. But again, all of these mechanisms are happening with the same chromophore. So this guy is really quite remarkable in its ability to do different things. So I'm only going to be talking about, we've looked at all of these, but I'm only going to be talking about this one and these two are all back in the animals. Okay. I have to be, I didn't, when I started doing this, I wasn't so specific about whether we were working on Coinor, which is basically the more efficient mutant of hadron, which is the original positive photo switching, reversibly photo switching protein. But I do have to be, because it turns out they're quite different in their behavior. So I'm talking about Coinor. Here's the spectroscopy. This is the off state. We irradiate that, we get this equilibrium, we can characterize as the on state. If we irradiate that, we go back here. It's cis-trans isomerization reaction. In Coinor, there's no excited state proton transport reaction. We can show that by just the simple excitation spectrum. If we look where the anion emission is, when we excite the neutral form, then we don't see any signal. So in this protein, no excited state proton transport reaction. We do the transient absorption measurements. Everything is dominated by stimulated emission. We do this global analysis, and that separates it into two fairly distinct lifetimes: sub-picosecond relaxation and a relaxation of about 7 picoseconds. There's always this annoying constant bit left at the end there. The reason for that is that you can't separate exactly the excitation of this from the excitation of this. There's always a bit of crosstalk between them, and that's I've got the wrong way. That state is highly fluorescent and appears strongly in stimulated emission. So it just lives for nanoseconds after the fluorescence lifetime. So that complicates things a little bit. But on this time scale, we get a small spectral shift and a change in the shape of this trans-anion stimulated emission as a function of time. So now we look at the time-resolved infrared spectrum, and the time-resolved infrared spectrum is a mess, really. We can pick out, this is the anion we talk about, so the chromophore bands are quite different, but there are still the four characteristic chromophore modes that we can see here. Everything else is a result of coupling between the chromophore and the protein. So these are all modes which, if you like, originate in the protein, but they're being perturbed by the electronic excitation of the chromophore. And there's a lot of them. I mean, there's about 7 that you can see clearly, but these have no equivalence in the chromophore at all. This one also does not. This one also does not. This one also, that's not a chromophore. So this is all, we refer to these as protein chromophore coupled modes because we couldn't think of a better name, although I would like to. Interesting thing is when we apply, just blindly apply the same analysis model as we applied to the TA, we get pretty similar time constant. We certainly get a biphasic type relaxation, which is good. But the interesting thing for us is that the dominant part of the fast relaxation is associated largely with decay of these protein coupled chromophore modes, right? This one disappears in the first stage. This one appears in the first stage. And this one largely disappears in the first stage. So it's as if these coupled modes are relaxing first, and then the excited state reaction is happening. So I mean, it's certainly a biphasic reaction. We have a Frank-Conver state, it goes to something else in the excited state, it goes to the excited state, it's stimulated emission, and then that relaxes back to the ground state. Is what the transient infrared is showing us is that this early phase is mainly associated with relaxation in these protein coupled modes. Okay, we can play the same game in transient absorption, running out of time, but that doesn't matter because it's basically the same story. Not quite as clear cut, but the time constants are rather different and they agree rather well between two systems. And again, it's the protein mode, if you like, which go first. That's just a summary slide. I guess the key thing that we pull out of this is that this isomerization reaction that we're looking at is not associated with just the chromophore relaxing in some kind of sticky environment. The environment, these coupled modes, are intrinsically a part of this isomerization form. Okay, so the surprising bit, I said there was no excited state proton transfer in Koinol. Koinol is a product of a few mutations from Padron. When I go to Padron, specifically Padron 0.9, which is kind of the original Padron, then we do see an excited state proton transfer reaction. Spectroscopy is almost identical. Photoacid behavior is a little different. But we're switching mechanism by just a couple of mutations, and most of those mutations are actually on the surface of the protein. They are so remote from the chromophore that it's hard to imagine they would have an effect. The only one we can imagine having an effect is this serine to phenylalanine transformation here. So when the phenylalanine is present, we get proton transfer, and when it's, well, measurements we've done so far, when it's absent, we don't get proton transfer. The key experiment, which we haven't done yet, is to switch one into the other, just specifically that mutation that we're going to do in the next couple of months to try to kill off this problem. But structurally, not very much has happened. Certainly not very much has happened around here, which you would think would be the key controlling component. All the action, however, when we look at the time result infrared spectroscopy, there are significant differences between these two and Hadron 0.9. I've just highlighted them here. We have no assignment for them, but there's one here and there's a couple shown. So apparently, again, single point mutations, which are relatively remote from the active site, can have a profound effect. In this case, a complete change in photochemical mechanisms. You don't have time to read those conclusions or probably the energy either. So let me just finish with the acknowledgements. As I say, the last part was all done by Anna, really great work, put a lot of effort into that. I don't make any of these proteins. I don't know how. These are my two collaborators from biology, Andras from Page and Pete from Stony. We've been collaborating for many years together. They find it hilarious that I still don't know the amino acid code. Why should I? The times of infrared measurements are not done in my laboratory. They're done at the Central Laser Facility, which simply, I think, maybe there are two groups who can do equally good times of infrared spectroscopy in the world, in Switzerland and in the UK, and that facility is run by Grant. I'll stop there. Thank you.
Okay, so you mentioned that there are distant amino acid mutations that lead to either excited state proton transfer or not.
Yeah.
And for that matter, even those colored motions.
Yeah.
So is there some specific kind of mutations that lead to those, as in I want to say, you classify them as hydrophobic interactions and things like that?
So our best guess for this transformation here is that this is a hydrophobic to OH. It's a phenyl group going to an OH group. Too far away to control things over here, but we think that probably that restricts access of water molecules to this side. However, we do have the structure. These structures do not show a significant difference in water molecule. But crystal structures don't show you everything. Particularly, they don't show you dynamic water molecule.
And sometimes the the unstructured that kind of loop region, those can change the water channels quite a bit.
Yep.
And that's why I asked about the hydrophobic.
So our working idea is that this is controlling water access. When we send that to referees, they say, well, where's the water? So, and that debate went on for quite a long time. But structure doesn't tell you everything, actually.
Sure.
We believe, so we're going to prove that this mutation has the effect that we think it does, and then we'll put it out there and say, okay, somebody should do the molecular measurement.
Yeah,
That's our hope, that this work will then stimulate some correlation.
I think for the next talk. My question is, these studies are done in solution basis. So now in this IRD, we have most of the things coming from water.
So we do everything in detail.
Oh, okay.
Yeah. So that's so then we go back to the lab and do the transient absorption. We do everything in H2O and D2O. Yes, we do the effect. But yeah. So often we don't mention this in talks, and I didn't today, really, which is a serious omission, because if you drink D2O, you die. So biologically, live, dead, that's a significant difference. So we should be careful
Yeah, because this week is really to
Yes, yeah, but we have tried, we have occasionally worked an extremely thin film, but the heat dumping effect is there.
So see, very interesting, the three ideas of what the chromophores can do: coupled, decoupled, negative. So the coupled positive one, which you said, that isomerization leads to proton transfer.
Yep.
So in that case, what my question is, you need to have a large electronic state change, when you say electronic rearrangement, electron density rearrangement in the chromophore to suddenly activate a pKa change that pulls a proton in. This is typically not seen in sylvine cases or other kinds of systems, although sylvines have quite a bit, those are examples sylvines can have. So my question to you is, and one of my students is working on this idea, that can you do this with radical cation mechanism, this isomerization? So can I expect for example, in confined environments, I can pull this trick off where I do the isomerization and couple to a proton transfer if there is a large
dipolar change, if there's hydroxide, we need a hydroxide. That's what I understand, kind of thing.
So I think you will, if you can make the confined environment extend the excited state lifetime long enough. So essentially, when we look at this guy in solution, even in solvents which should be quite good proton acceptors, we never so in water, we never see excited state proton transfer. But that's because the isomerization happens in 200 femtosecond.
Yeah.
That's it's just out competing in it.
Yeah.
Is what we have done is actually put two fluorine groups here to make it a better photoacid.
Yeah.
Then we see that we can initiate I think it was a 60 femtosecond excited, well, 60 femtosecond lifetime. So there was maybe 100 femtosecond excited state proton transfer reaction in that case. If you confine it, so if we freeze it into a glass, here the lifetime is 3 nanoseconds.
Of course.
So then you might get the proton transfer reaction.
But this is a neutral chromophore emission. This is not the anionic form.
That's right.
So my question is, can I induce, it's like proton coupled electron transfer. Electron transfer leads to proton transfer. So can I do isomerization leading to proton? So it's coupling of the isomerization to the proton transfer coordinate. So
I was thinking you probably could.
but you need to.
But you've got to create, but then you have to create the radical cation in the ground state.
Right.
Or
in the excited state, then I do the
if
isomerization.
you're doing the excited state, then that will quench.
Okay.
And you won't get the excited state proton transfer. But you might get the proton transfer in the ground state.
Okay, yeah, in the ground state. Yes.
So, when the proton transfer in the excited state was like 20 picoseconds, right? First,
Yes. Yeah.
but the back transfer was in nanosecond.
Okay.
And you mentioned that there's a huge kinetic isometric there.
Yeah.
Now, why is that? Is it related to pKa differences between the carboxylic acid and the excited state chromophore and the ground state anion?
Yeah. So I think that there could be quite many. Get to it. So the potential energy surface.
No,
associated with this,
Yeah.
quite long, because there are 3 states, then it's kind of lumpy. And the same would be true in the ground state. The assumption is that because the excited state is no longer there, then the barrier heights are slightly different, slightly higher in the ground state. And that's what's slowing it down.
But the dynamics of the water would not matter, right? Because I was thinking when you do the proton transfer, the orientation of the water have actually changed.
Yeah, yes, you're absolutely right. So that would be a change in the proton line. So the water is now pointing in a different direction.
And that would also lead to your isotope effect.
Yeah, no, that's also true. Yes. Yeah. All right. Okay.
Next question.
So Steve, you said there's a large isotope effect, there's proton transfer.
Yeah.
What is the isotope? Like how big is it?
So on the forward reaction,
You say it's the process is tunneling. So what fraction is tunneling?
well, yeah, so
That
that
means 100% is not.
I haven't done this myself, but Paul Champion has done quite a lot of, actually a huge amount on the tunneling reaction as a function of temperature. And then he gives on this chrome.
On this one?
On this chrome. Oh, I know, on,
So what is this? 1.4 then? or-
so going for the forward reaction.
What I find surprising is to say it's tunneling. Wow, because I mean, then none of these motions matter, right?
Yeah, so it's not,
So I mean, if it's really tunneling, that's in a narrow barrier, right?
so it would not be purely tunneling, but forget the isotope effect. So the isotope effect is, from memory, sort of 5 or 6 fold, which is significant.
So people can like, is the barrier really that narrow that
I think
significant?
it's still an activated process, but they talk about the tunneling at the top.
It's
of the barrier.
activated, it's not tunnel.
So there's a long discussion of this.
That's why, this isotope effect came up, because is it really tunneling? I mean, that's.
Well, then what else?
I give you a slow more, I.
Yeah, but indeed, but then, I mean, you may have seen this in enzyme catalysis.
Yeah,
There's a big debate on what's
generally, proton transfer processes can have large transfer effects without any tunneling. It all depends on
The distance.
the distance and arrangements in the variable. So we have encountered 10,
But
12.
not necessarily large
When you
isotope.
give, when you just, then you say it's nice to effect, you would temperature dependence and temperature. Temperature dependent on the.
The ones which were carefully done, the temperature dependence of it.
but the mechanism is not tunneling?
No, it's just, you can check, this is very, very documented, it's standard 750.
The temperature.
There's a isotope effect of 10. Okay, if you change from H2 to B2O in a proton transfer state. So that actually does not involve any number.
So it's just a.
It's just,
a weak hydrogen.
it's
bond.
Is this the distance or the?
tracking trenches. Right.
I just have a quick follow-up on this question. So when you change the structure, the proton transfer rate increased by, orders of magnitude, like 200 femtosecond. So would you expect tunneling on that, that short time scale?
That was the forward reaction, the backward reaction didn't.
Was nanosecond, right? Backward reaction was nanosecond.
Yeah, so, but here this is a bad slide, but, so this is the wild type, and this is the one where we damaged the proton wire, and they have the same back reaction. So 17 here, 20 here, pretty different. This one, this is a different protein altogether. So apparently, these two have the same rate determining same barrier. We haven't done the temperature dependence. It's the hundreds of picoseconds which changes here, but we believe that that's because just indeed the distances have changed a lot now. So I don't think we didn't measure the kinetic isotope effect on that. I think it has been measured by Dan Woodland, but
Not in particularly GFP protein, but in small molecular system like HBQ or HBT, people have done some, isotope effect, and for a slower reaction, like picosecond scale, they have seen tunneling, but for hundreds of femtosecond or 10 femtosecond time scale, no tunneling effect. Or isotope effect.
Yeah, so I think that if you have, essentially if it's barrierless, then you wouldn't expect a tunneling. You wouldn't expect an isotope effect, but as soon as there's a barrier there, then it becomes possible.
Okay. Any other question, comments? Okay, if not, let's thank one. Small token of appreciation from our side.
Thank you.
Thank you. Yes. Yeah.
They didn't have that sign up, right?
Yeah.
Sorry about that.
That hasn't changed.
Okay, so
Actually, no, that's.
our next speaker is from Indian Association for the Cultivation of Science, Professor Abhishek Ray. He is a leader in bioinorganic chemistry. He does different kinds of synthesis of inorganic molecules, metalloporphyrin based molecule, and does multi-electron transfer and multi-proton transfer reaction. And he will share some of his recent exciting results with us. So,
Thank you very much. It's not recent, it's like a story. It's been going on for 15 years in my lab. Thank you, Jerry, for putting this together. Actually, nobody knows why you are so successful in organizing conferences in short notice. Let me tell you the secret. See, Jerry is by far the most popular chemist in the country. And that goes without saying, that's an established fact. And anyone who knows JD knows he's a happy person. And that's why people refuse to tell no to JD, because they don't want to see him become unhappy. So if you ever want a conference to be organized, get it. He's going to get anybody you want, simply because everyone wants to see him smile. All right, what I'm going to talk about is an area that we have been developing in our lab right from the beginning, early stages of my career. I mean, it sort of hovers around how to do bioorganic chemistry with small molecules on electrons. And I'll tell you why we want to do this, why all of a sudden we need to invoke electrodes and bioorganic chemistry at the same time. Now, you see, they did touch upon the bioorganic chemistry, the ideas that we generally use in this. So when you look at a metal enzyme system, previously people were mostly focused on making the skeleton of what is known as an active site. This is an example of the hydrogenase enzyme, which makes hydrogen or oxidizes hydrogen in nature. If you look at the active site, there's an organometallic active site with two ions or bridging dithylate ligand and all that. So that's your basic active site geometry. But as it has been the theme of today's symposium, you can see that interactions from the outer coordination spheres attenuate the function of these active sites. And if you do not incorporate them, it is highly unlikely you're going to get function similar to that of a protein. And Debu was being generous to inorganic catalytic systems when he said we could get 100 turnovers. No, people couldn't get 100 turnovers. People could get fractional turnovers most of the time, as he did point out during his PhD days. Then it improved to 1.5 to 2.5. Now, of course, the organometallic chemistry, they get much higher turnover, which is why they are in industry and they're rich. If you're going to a conference and you see who's sitting in the business class, that's an organometallic chemist or a polymer chemist. Definitely not inorganic chemist. All right, unless, of course, you're a dinosaur. That's different. All right. So that's the whole point, to actually understand these weaker interactions well, and then go into modeling these systems, which I think is pretty good. In my book, we actually try to understand reactions that require multiple electrons and protons. I've passionately named them MEPs for no reason, MEPs. Now, these reactions are ubiquitous in nature in all kinds of systems. For example, oxygen itself can be reduced by 4 electrons to different species. And I'll show you in a few slides from now how this is very nicely managed in nature to give rise to in different metal enzymes. Similarly, nitrite in nitrogen cycle can be reduced all the way to ammonia and through different intermediates. Similarly, SO2 in sulfur cycle goes all the way to H2S through different intermediates. The whole point here is if you look at these different intermediates, they depend on how many electrons and protons have you added to the parent molecule. So you add single electron to oxygen, you get superoxide, down 2 electrons peroxide, 4 electrons H2O. And the whole point is, can we control these reactions in artificial systems and be selective in doing so? And this kind of multi-electron, these MEPs have become very relevant these days because of the problem of CO2 reduction, which is again a reaction that can give you different products, and they all vary between in number of electrons and protons that you give in such. Okay. Now, as I said, I spent my grad school in understanding enzymes and how they work. Now, in metal enzymes, proton transfer is controlled by lesser residues, for example, classic peroxidase. Actually, the isotope data I was telling you about, you get much better isotope data on peroxidases. There's a huge literature on it. So, for example, horseradish peroxidase, they require a proton to split H2O2 to generate a highly oxidizing intermediate. I'll get that. And it actually uses histidine and arginine near the active site to deliver proton to the reaction center. The way it controls electron transfer is by controlling electron transfer rate from reductase enzymes, which are single electron reductases, NADH based or iron sulfur cluster based. And these deliver electron at very specific rates during a reaction cycle in a controlled manner. So this is how nature does control proton and electron delivery. Okay, now, this is a slightly complicated slide, but let me tell you how nature handles oxygen. So for example, oxygen cross diagram, different oxidation states are possible. And this is oxygen that keeps us alive. 1 electron reduced superoxide is ROS that kills us. And that's sort of relevant to life and death, actually, think about it. Whatever keeps us alive is also what is killing us. So this is difficult to control, this chemistry. However, heme proteins in nature, they have come up with very elaborate ways of doing this chemistry. So for example, the ferrous form of hemoglobin can bind oxygen. It binds oxygen, make a ferric superoxide species. This is then for this oxygen reduction cycle I'm taking you through in cytochrome C oxidase here. This superoxide gets reduced to peroxides. Peroxides cleave OO bond, generate high valence oxidants. This then get further reduced by electron and proton transfer to generate iron 2. However, the species that are generated, and you can hit some proton.
It's not working?
No.
Turning on and off again and.
He's a battery.
It's not a battery issue, there's a connection issue. Right, so, thanks. This iron 3 superoxide species, which is an intermediate in oxygen reduction, is utilized by enzymes like indole dioxygenase and tryptophan dioxygenase to oxidize organic substrates. And I'll tell you a little bit more about this in a while. Then this peroxide species are present in cytochrome P450s, which can act as an oxidant as well. This compound 1 species, as it's popularly known, is present in cytochrome P450 and oxidase peroxidase that can oxidize organic substrates. So the same the species present in oxygen reduction are populated in different enzymes and used to do their oxidation chemistry. So it's basically the same, okay, the species that are involved. Now, this will become important down in the lecture. In our body, we have an oxidase, which is heme-based, and this is cytochrome C oxidase, which reduces oxygen to water. Is a heme system that does so. This is responsible for respiration in complex form, and it drives the oxidative phosphorylation process. Now, other than that, we have in our body oxygenases like cytochrome P450. That's essentially metabolism in your liver, hormone synthesis, drug breakdown, anosynthesis, all of that done by this superfamily of enzyme. Apart from cytochrome P450, we have this heme enzyme, which is known as tryptophan dioxygenase or heme dioxygenase in general. This actually breaks tryptophan to generate this kynurenine derivative, which starts the kynurenine pathway, which is a target for cancer therapy. And it's a source of nicotinamide in our body, which leads to formation of NAD. So all the nicotinamide in our body, all in our DNA and everything, comes from tryptophan through this path. This is a very important enzyme as well. And this is, for example, another version of cytochrome P450, also known as aromatase. This is involved in hormone synthesis, and this is also in our liver. Now, these three enzymes, this is the one that's going through all the intermediates that I showed you. These three enzymes use different iron oxygen derived intermediates as their oxidants. This indole dioxygenase or heme dioxygenase uses this iron 3 superoxide to do this chemistry, cleavage of this CC bond. Aromatase, the cleavage of this CHO decarbonylation is done by this peroxide species. And the most stringent oxidations of cytochrome P450 are carried out by this compound 1, which is iron 4 oxo with a cation radical on the point ring. But they are all derived from oxygen during oxygen reduction. Generally, how people approach this reaction is they would create molecules that looks like that inside of these enzymes. So, for example, Jim Coleman, Kel Carlin, Naruta, they made this beautiful synthetic iron porphyrins with copper on top. And these are very difficult to synthesize, 30-40 steps, but remarkable work of art, if you ask me, to get there. And they did get there after 20 years of struggle. This is what and then they would use this to reduce oxygen. I'll come to that. On the other hand, if you look at work of J.D. Groves, phenomenal contribution from his side, where he actually could generate this high-valent iron oxo-manganese species for peroxides, and they would use it to oxidize for substrates. This is what normally people will do. But it's very difficult to get catalysis under these conditions. And that's mainly because once you make these compounds, how you're going to do the chemistry. So imagine I'm trying to reduce oxygen to water. So what I need is oxygen, I need protons, I need electrons, and I have a catalyst. The principle, if I take the catalyst and I add oxygen and electrons as a reducing agent and protons, will the reaction work? It never works. And that's because when you try to put all these three components together in a homogeneous solution, what will happen is they'll react with each other. Your reducing agent will react with proton to make hydrogen. It will independently react with oxygen without going to your catalyst to make superoxide. So it's a mess. Apart from that, in homogeneous solutions, you see dimers being formed. This is a very famous problem in Portland literature. You have this superoxide species after oxygen binds ferrous dioxygen, and this forms a dimer, and this is catalytically dead. Similarly, the superoxide species can be hydrolyzed, generating oxygen and H2O2, then Fenton chemistry turns on. So there is an issue why these things would not be made catalytic under homogeneous chemistry. The other way people evolved, and this is Fred Ansel in Caltech in 1970s, what he showed is actually in principle, you can take these iron porphyrins, you can adsorb on a graphite electrode, and then you dunk it in water, and do this chemistry in water. The advantage is the electrons are delivered by electrode, and your catalyst is on top of that, and all you get from your aqueous medium are oxygen and protons. And that has worked well. And you get this beautiful, this is called rotating disk electrochemistry. You get this electrochemical response that you can analyze its CAT-HT and Levitch current components, get rates and everything. Now, before I started, what we knew is that PH7, you can use this elaborate heme copper models, and you can reduce oxygen reasonably with reasonably high selectivity to water, and the second order rates were around 10 to the power 5 moles per second. Now, this was the status before I started. The problem was there was no idea about the mechanism of the reaction, because how do you probe a heterogeneous catalyst while it's reducing oxygen? So this is standard cyclic voltammeter response of a catalyst put on an electrode. And once you have oxygen and protons and you reduce the potential, what you will see is the oxygen reduction current. Now, over here, you have some kind of mechanism going on. The point is, how do you investigate that mechanism? There is no good way of doing this. And more importantly, if your electrode is static, then what happens? The reaction is controlled by diffusion of oxygen, protons, etc., from solvent to the electrode. And so it's very difficult to get any mechanistically useful information out of this. So what we did, and this is still introduction, we developed a method where we would use this rotating disk electrode setup and a Raman-based method to investigate these catalysts in situ under catalytic condition. So imagine your catalyst is in a catalytic steady state. You have this, there's a tip of this electrode over here. This is gold or silver, and we form a self-assembly mono layer of thiol on top, and then we attach the catalyst to this. So we have a single mono layer of catalyst. And now imagine it is doing a steady state, it's at a catalytic steady state, doing its catalytic, going through its catalytic cycle at an applied potential. We investigate the system with Raman. There's a homemade electrochemical cell where we have an optical window at the bottom. Here we put in the laser and electric scattering, put it on put it in a spectrograph. I'll show you the picture before. And what happens is during catalytic condition, different intermediates are going to be formed and accumulate by different amounts. And the idea is, if we can identify the species, then we will know what is the rate limiting step of the reaction. And that's where Raman becomes very handy, because porphyrins have they show results on effect because they have a very intense, they're very intense chromophores. And on top of that, when we do it on top of silver thiol surfaces, we get the surge effect as well, which allows very high resolution data. I'll show you. In single layer of catalyst, you're looking at picomoles per square centimeter. Now, this is how the system used to look like when we made it. If we had submitted a picture of this along with our manuscript, I'm sure it would have been rejected. Nobody would believe that you can get any reasonable data from here. But then we started getting more money, and now initially what used to take us 20 minutes to acquire data, now we can get it within 1 minute. So we're pretty good in terms of signal noise now. Okay, so what we did is we studied oxygen reduction by this series of iron porphyrins, including some heme copper proteins that we got from our collaborator EU in Urbana-Champaign. He used to be in Urbana-Champaign now, he has moved now. And then we investigated the reaction mechanism in situ. And what we found is, across the board, the species that was rate limiting, that was accumulating on the electrode during oxygen reduction, were peroxide species. So this told us something fundamental, that the fate of oxygen reduction by iron porphyrins or heme copper systems or heme copper proteins depended on the fate of this particular species. There's a low spin hydroperoxide species which is formed by oxygen reduction. This species, essentially the cleavage of the O bond is the rate limiting step, which is why they accumulate under catalytic steady state. Now, this species has two fates. You can either protonate it on this oxygen, which is bound to iron, that's a proximal oxygen, or at the distal oxygen. If you protonate in the proximal oxygen, you give H2O2, that's a 2-electron 2-proton reduction product. If you protonate on the distal oxygen, then you get cleavage of the O bond and water, that's a 4-electron proton. So it's the site of protonation that decides selectivity, and it is in general cleavage of the O bond that determines the rate. With that insight, what we did is we took inspiration from the peroxidase model and we made iron porphyrins which can selectively deliver protons to the distal oxygen, the corner wall, right? And here is the structures of this iron porphyrin, and as was mentioned, we do spend a lot of time in synthesis of these iron porphyrins. Now, I'll focus on this one particularly in the next few slides. This one is a pendant pyridine, which has a pK of around 6. So at pH 7, we get partial protonation of this at the least. Now, if these are good at cleavage of O bond, what we did is we took this series of iron porphyrins with this pendant protein, pendant pyridine or amines, and there's a control sample which has no nitrogen, and we investigated cleavage of peroxide. This was done with peroxybenzoic acid, peroxybenzoic acid, and we investigated the generation of this high valent compound 1 species, which is this EPR, which we had to go to Grenoble to collect. And we looked at the kinetics of this and how these species fare. So, if we take this normal iron TPP with peracid, it just decays, it doesn't do anything. Now, given the previous work, these are hangman porphyrins from Danusera. Because the reactions are done at a different temperatures, I've normalized the activation barrier. This hangman porphyrins of Danusera generally have activation barrier of 16 kcal. Horseradish peroxidase activation barrier is around 13 to 14 kilocalorie. Now, this particular species, FeL2 with the pyridine, that's right over here, here the barrier is 12.7 kcal, which is much lower than hangman porphyrin and not similar to that of natural enzyme. The one with the primary amine, that's even lower, that's at 12 kcal. So these are really fast. And the moment we remove the pyridine and put a benzene over here, you see the barrier goes up to that of hangman porphyrin. So essentially, these are very good at shuttling proton and cleaving the monoperoxide. Since we knew this, now we went ahead and checked, okay, how about oxygen reduction? Does it do any better than all the heme copper systems that were reported? So this is the rate of oxygen reduction, normalized second order rate to 10 to the power 7. These systems from Coleman and Cardin, they're over here. They're in the order of 10 to the power 5. But if you look at this guys, they are actually 10 to the power 7. They are at least 500 to 1,000 times faster than the heme copper systems that were previously used. And as far as selectivity is concerned, these things produce very little H2O2. They consume most of the oxygen to reduce it to water. So indeed, this proton transfer residue can facilitate the O-bond cleavage, which of course we figured out after we did the histogram. All right, now we could improve this. Understanding mechanism by the method we developed, we could enhance the rate and we could enhance the selectivity with much more simpler systems. Now, this is where we did our, at this potential where it's mass transfer limited, we did the SARS-RD as we call it method to investigate what was the mechanism of oxygen reduction. Now you see this is a potential dependent region. So here there is a redox process involved in chemically speaking. So what we did is, okay, this is how our system looks like. I know I've been a little vague in terms of what we're doing. So you have a silver surface, attached to it is a thiol, and it's terminated with an imidazole in this case, and you have an iron porphyrin attached to it. And then the rest of the surface is filled with octane thiol or some other diluent thiol, which does not have anything to bind the porphyrin. And we use different types of porphyrins and linkers. Now this data I'm showing you is one where you have imidazole bound, okay? Now, what we do now is we collect Raman at different potentials. So this is your oxygen reduction current. And you can see as you lower the potential, the oxygen reduction current goes up. At around minus, let's say minus, at minus 100 millivolt against silver chloride, what you see is as you lower the potential, initially a peak comes up at 571 right now. Then as you lower the potential further, this again goes away. A new peak comes up when this goes away over here at 668, which then again goes away. Here, along with 668, another peak comes up at 816. And then finally, at lower potential, you see another peak at 790. Now, these features are then confirmed using O18 isotope leveling. So these are in blue are the O16 data, in red are the O18 data. So at minus 100 millivolt, you see this 571 that shifts to 546. We also see something at 1117 that shifts to 1052 with O18. So this implies we are forming iron 3 superoxide species. Then as we lower the potential to minus 0.3, this goes away. We get two new sets of vibrations, 668 and 816, both O18 sensitive. That represents a low spin iron 3 hydroperoxide species. And at a lower potential, this goes away. And what we see is 790 to 762, that's consistent with the iron 4 oxide species. So we actually can construct a catalytic cycle based on and how the species vary depending on the potential we are applying. Now, if you remember how I did mention you that these are different, these intermediates, the superoxide, peroxide, these are oxidants in different enzymes. Now we have a way of generating this oxidant from molecular oxygen by controlling the potential of electrolysis using this imidazole bound picket-fence porphyrin system. And I'll get to this in a minute. So this is what we do now. We keep 2-methyl indole, that's a substrate analog of tryptophan, and then we hold the potential at minus 0.2, and we see this cleave the CC bond and generate the chimeric analog. And if you look at these are different species, how they vary with potential. This is the iron 3 superoxide, this is the iron 3 hydroperoxide, and this is iron peroxo, and this is the yield of the chimeric with potential, and it almost matches that of iron 3 superoxide. So the reactive intermediate is iron 3 superoxide, and they will use for you turnover number of 40,000. That's with molecular oxygen. So we can do it a little, not million, but definitely more than tens and hundreds that we used to see when we were students. Now what we do is the same system. We change imidazole to thiolate. Now thiolate is the actual ligand of picket-fence iron cytochrome P450. Okay, and then we do the same investigation. We study the species being formed during oxygen reduction, and with isotope leveling, we can confirm that we are seeing something at 579 go to 553 and 798 go to 757. That's very indicative of a thiolate bound iron 3 hydroperoxide species. Okay, so now we have a hydroperoxide species thiolate bound, and the reason why it's important is okay, I'll tell you in the next slide. So here's the distribution of species that we see. Iron 3 superoxide with thiolate, we form iron 3 hydroperoxide, and this would automatically invoke formation of this guy because the pK of this is very high, easily gets protonated at pH 7, generating this high valence species. But nonetheless, we have in case of thiolate bound iron porphyrin, we see iron 3 hydroperoxide with the thiolate. Now, this iron 3 hydroperoxide with the thiolate is the oxidizing agent in the enzyme called aromatase. Now, one of the most fundamental questions you will ever hear as a young person is male and female iron, right? Now, of course, this mystery of how they are different will never be solved, but chemically, this is the male hormone, this is the female hormone. The female hormone is more oxidized than the male. So, if you want to make the girl happy, say you are more oxidized. And if you want to make her happier, say I'm more reduced. Both will convey the same message. Now, in this pathway, there is this one particular enzyme called aromatase that does an enzyme called a reaction called decarbonylation. It cleaves this CHO group to release formic acid and this radical over here. Okay, and this is this is called hemiacetal. This is a peroxo hemiacetal intermediate. This is a hemiacetal with a peroxo, which is proposed to form. Okay, now There are reports of this chemistry in non-heme iron, in non-heme systems, Swallow and others. And they have shown this reaction works in non-heme system with known peroxides. And it forms this alkyl radical, which can either pick up a proton by HAT to make the alkane, or oxygen ion transfer from oxygen to make the aldehyde. I'll not stress on it too much. Now, just reminding, we did observe the hydroperoxide species thiolate bound iron porphyrin during oxygen reduction. Now, what we do is the electron transfers are lower in the hundreds of second inverse. So that's important. So what we decided to do is, because we saw this iron 3 hydroperoxide form in P450 type systems with the thiolate bound porphyrin, we know they very easily get protonated and cleave the O bond. So what we thought is, what we can do is, maybe the next slide. What we can do is, we can attenuate the electron tunneling rate from the electrode to match the electron transfer rate of reductases to our active site. And that would give this high valent oxidants enough time to actually oxidize the substrate. So we call this an electrochemical analog of cytochrome P450. The whole idea is, normally under fast electron transfer, your iron porphyrin will reduce this high valent species very quickly to do oxide reduction. But if we reduce the electron transfer rate to this species, we should be able to turn on a monooxygen state reaction. So normally it would take electrons and go, but if we reduce the electron transfer rate, we might be able to do this reaction. And indeed, that's what happens. What we do is, when we reduce the electron transfer rate to like 500 second inverse or so in our thiol model tunneling rate from gold electrode to the porphyrin, we see oxidation of very inert CH bonds with a very high turnover numbers, epoxidation, all with molecular oxygen. And so we are indeed getting monooxidase activity during oxygen reduction by slowing down the tunneling rate to the catalytic site. And here, this is a solvent isotope effect of 13, which comes from protonation of this species from bulk solvent. And because there's a hydrophobic environment under the porphyrin, this proton transfer is slow. It's not very well organized. So we get a 13 isotope effect on proton transfer. Now, we went ahead and did some more experiments. We took different types of CH bonds. This is primary, this is benzylic. This one has tertiary, secondary. This one has only secondary CH. What we were very pleased to find is, for example, here, the only product was this cyclohexanol. There was no over-oxidation. Now, in principle, this CH bond is easier to oxidize than this CH bond. So there should have been some over-oxidation, but we didn't see anything. Similarly, in this case, we actually saw oxidation of secondary more than tertiary. Okay. So the reason why we thought this was happening is because we were using this iron porphyrin with a bulky, sterically hindered pocket. The thiolate comes from here, and only sterically unhindered CH bonds had access to the active site and were getting oxidized. To prove that, we just removed two of these steric hindered groups. And once we do that, all the selectivity is lost. So the entire selectivity is coming because of the sterics of the iron. So this is what I wanted to tell you. By understanding the mechanism in situ on heterogeneous electrodes, we could actually harness the oxidizing potential of intermediates produced during oxygen reduction by judicious choice of proton transfer in the porphyrin and electron transfer rate by controlling the tunneling rate, and get very lucrative chemistry with molecular oxygen, which so far has been actually, I think, what was the term Harry used to use? Holy grail of bioinorganic chemistry, using oxygen as an oxidant and being selective about it. And I think maybe we are 40 years late after Harry, but we are getting there with substantial reactivities and encouraging selectivities. And thank you for your time. Thank you again for the invitation.
Yeah, okay, fantastic work. I have this perennial question, why things suddenly move with higher turnover number on the electrode surface. So this is one part of the question, but then I go and see that the turnover numbers are great, but the turnover frequencies have improved from the catalysts that people had made, but in many cases, those catalysts had higher turnover number, but turnover frequencies, but shorter turnover numbers, that is lifetime of the catalyst was compromised in many cases, previous generation. So this one, in this case, if you have increased both to slight extent, but can you?
Previously, there were no catalytic reports where oxygen could be used as a oxidant.
Yes, I'm just talking about general catalyst, but
Yeah, so let me tell you where the difference is, and the difference lies in the approach altogether. You see, normally what people would do is what we did here. They will generate the species and then have that react with a substrate. We are not doing that. What we are doing is, when that's in the scheme of SURS-RD, our approach here, and that's where lies the main crux. You see, when we do this chemistry, we do it under catalytic steady state. So imagine this is my iron 2 porphyrin. It reacts with oxygen to make iron 3 superoxide. This then takes up protons and electron to become iron 3 peroxide. This then takes electron to make some high valence species, which then collapses to iron 3. Now, when you do, what we are doing is, the system is in a catalytic steady state, which means these concentrations build up depending on which has a slower or higher barrier of decay and a lower barrier of formation. The trick is, we are not using a single molecule. We are using this dynamic population of these oxidants as our catalyst. So when we are putting an organic substrate, depending on the reactivity of the substrate, it's either going for the superoxide, or it's going for the peroxide, or it's going for the compound 1. So it's not that the same molecule is turning over.
So that's where
Part of-
molecule helps.
Part of the population reacts, but this is again regenerated immediately because there's a catalytic steady state of oxygen reduction. So all of this is happening during oxygen reduction. These are not happening like as independent catalytic steps. During oxygen reduction, we can control the population of this species by changing the porphyrin, the action ligand, the electron transfer rates. And thus, we can harness these species which are accumulating on the electrode for as oxidants.
The turnover frequency will be dictated by the time scale of the electron injection to the electrode. In some sense, when you're creating this population, it's the electrode that injects that electron. So
No.
if electrons, for example,
No,
there
here,
are partners.
hold on. When you see this electrocatalytic current, okay, right over here, the current is electron transfer rate limited. Over here, the current is mass transfer. So when we do the catalysis here, electron transfer is very fast. Over here, we have done that, so here electron transfer will be regular. But generally for these reactions, the individual reaction states in the catalysis, for example, this superoxide breaking the CC bond, they are much slower than electron transfer or proton transfer. So the turnover frequency that you see will be dictated by that chemistry. Okay, because they are much slower reactions.
This is really own precision chemistry. Now, so if you take the thought experiment, so you are able to sit at a particular voltage and generate the correct species that you want, iron oxo, peroxo, superoxo, if I'm correct.
Yes,
And
you are
so
correct.
now if you take the same substrate and change the potential, can you get different products?
Yeah,
Where is that?
that's what we're doing. Now what we are doing is we are doing cascade synthesis.
Yeah.
So do reaction with the superoxide first,
Yes.
and then use the hydroperoxide to do something, and then use the compound 1 to do something. Because this is sort of like how steroid synthesis is done. First this, second that. So now what my students are doing is they are looking for good substrates, and that's why I wanted to show this to Debu to get his idea on what we can do. That where we take one substrate and do a serial reaction, and what we can also do is we can set up a reactor with subsequently different bulky resist chambers. So do one reaction here, then transfer the material to this and do the second follow-up reaction there. So there's a lot of engineering you can do, but you are absolutely correct, that's what we do.
Yeah, I have question like really your metal. Is there any reason for which the silver that
Oh, yes, the silver that we use is only for the Raman experiments. Because the silver resonance, plasma is around 400 nanometer, which is close to the soda kind of iron porphyry, which is around 400 to 420 nanometer, which we use to get the resonance number. So it's the combination of the silver plasma and the charge transfer of the porphyry that gives us around, I think, close to 10 to the power 30. Which is why all the Raman data you saw, for example, these data are on a single layer of chemistry on an electron. That way it's pretty good.
But when the sulfate comes out, right, it's like on a silver, unlike gold. It's a,
Well, I would say let's not rush to those definitions very quickly because if you look at the literature of chemisorption versus resorption, a bigger question with this kind of question is Thiol and metal interface is the protonation state of it.
Yeah.
That's what that is, and we actually did deal with this around 2013 or 14. We did a series of papers where we showed that 30% of the thiols on a flat gold electrode are protonated, and 70% are deprotonated. So we use a combination of Raman spectroscopy looking at the SH vibration, and then XPS data looking at the ionization of thiol versus highlight, and that's how we concluded that. So around 30% of that, that's on a flat electrode. Okay, is protonated, the rest are deprotonated. On a flat surface, on a spherical surface, it's all deprotonated.
when you say deprotonated, it is like something that you have got from the.
Yes, minus, yeah.
So now that's clear. Now, that is the case, silver will use the surface component behavior, right? Once we have the, instead of having a flat metal.
No. That's what I'm saying. Silver that we're using, that is rough for to get the surface. That's not the flat surface, which is why I'm always saying the gold is a flat surface. The silver is a rough surface. And that's what we use to probe the mechanism, because otherwise I will not get the sun back to hydrogen. Then again peroxide. So that was kind that we could do. Right. So what we are doing here, what we do, you would call reductive activation of oxygen. So reducing oxygen first to generate oxidizing species and then using that for oxidation of organic species. Now, this is difficult to do in homogeneous solution because in homogeneous solution, you're going to, the biggest problem is dimerization. Right? You have a non-heme or heme iron 2, you add oxygen, then will form. But on the surface, we have these porphyries which are surrounded by just bare clouds. The next porphyry is far away. We control that dilution, and we know that from cover XPS and different techniques. So they can never dilute. So that gives you a huge advantage, site isolation, which is like the protein network. So that's the advantage.
So I was wondering, vast majority of your work is on film systems so far. Let's say cyclone type of system, but aluminum or maybe alone and others are using like more of a non-film system. Have you?
No, the thing is, I won't say I haven't put thought in that, but because I'm doing bio-inorganic chemistry, I would like to stick to ligands that are available in nature and not look for ligands which are, for example, this is my bias, that I want to do chemistry with porphyrins because it's heme, it's there in nature, it works in nature. If we try and understand how it works, we can do it. And see, one of the things is heme is not toxic. If you ever want to use heme for any application, you don't have to worry about toxicity because our body has ways of dealing with heme because we have a lot of hemes now. Right. But then if you go for a lot of pyridine containing ligands and everything, and you want to actually scale up and use it, you're actually dealing with the toxic species. So that's also something that advantage lies with using porphyrins for doing this kind of chemistry. So that's a philosophical take why I do porphyrins and not non-heme. Scientific take is better chromophores, faster electron transfer, much more stable ligands.
Thank you. Amazing.
I have a very quick question. What is the basis of assigning those vibrational modes to different intermediate species?
That's a very good question. I did not cover that in the introduction. Okay. Protein literature. So all the vibration that I'm doing rests on the work done by Raman spectroscopists on heme enzymes. That would be Jim Kincaid, that would be Kitagawa, that would be Tom, I was thinking Tom, Tom, Dick, Harry, Tom, and, no, we have a Tom, Dick, Harry of Dynamite. Tom Speedo, Dick, Tom, Harry, Gray. So I used to joke when I was student. And this guys, and actually also, Paul Champion. He was the first one to show the iron sulfur vibration inside of a 450. So it's based on the work that they have done, where there is a database, where you can look at the vibrations on isotope shift, and you can conclude with reasonable confidence that's what that is. Now, I only showed you the metal ligand stranges. Apart from that, the porphyrins have ligand vibrations. Ancona referred to that in the ligand. No, not you. I think you talked about the porphyrin vibrations in the myeloglobin.
Right.
And they are very sensitive to the oxidation state and the spin state of the iron metal in the porphyrin. These are characterized by Kitagawa and Spear. And these are new 4, new 2, new 3, all those vibrations. And they are also there in that. So when we see iron 2, we can see the whole new 4 new 2 become like iron 2 porphyrin. Then when it's iron 3, it becomes iron, when it's low spin iron 3, it goes to low spin iron. So we use a combination of the porphyrin bands, marker bands, and the isotope sensitive metal ligand bands to converge to the species.
So in presence of the electrode, so you could also have the vibrational Stark effect, right? So that would shift the peak position as you grow.
We have measured porphyrins on electrodes and compared our measurements with porphyrins in organic solutions. We have not seen any difference to suspect that there is any electronic communication between the electrode Fermi or the plasmonic layer and the catalyst. They're separate enough, I suppose.
No, but I think John Gelati from University of Southern California has shown that
They use
pretty narrow.
It's very short.
Vibration, and it's very close to the.
Right. So this long thiol, they dampen all of it. And it's tricky because, for example, we use octane thiol, we see lovely surge. Butane thiol, we see surge, but then we see electron communication. We go to dodecan thiol, all the surge is gone. So we are hanging the balance here.
Okay, any other question, comments? Right, if not, please thank you.
So, yeah. Oh, God, yeah, God. Consider given one of these ones, the real artist.
Okay.
That's very expensive. Of course, which is why I asked.
Well, other words, Diksha?
Yes, hello everyone. Good to see.
Yeah, so first of all, just let me say a couple of words, Diksha. Just give me a second. So we will have an ACS session right now. First of all, thank you both the speakers of the session. It was fantastic. I'm always amazed by Steve's kindness and Olufek's wit and intelligence. I'm very, it has been very fulfilling for me to see all of you. So thank you, Steve. So we have this special session with Diksha, who has supported this particular short symposium in no time. It's absolutely Diksha and Ajay were, when I sent that first email, they said, yes, let me look at it. Ajay said, let me look at it. And they responded within a couple of days that they will support this. We are having a little bit of a dinner, Diksha, for that. So thank you for feeding us. But I just wanted to say that Diksha has been one of these people that I've met in my last 15 years who has sort of shown tremendous interest in pushing science communication in all different ways. First through RSC. She was actually an RSC affiliate before she joined ACS. And we all remember, some of us in this room, remember Diksha attending Kaleidoscope meetings and supporting Kaleidoscope for the first time through RSC venture, but then she came back through ACS and supported Kaleidoscope multiple times. So we have known her to be very generous in supporting any kind of good scientific meeting, which allows discussion for some time. This was a 10-minute quick Q&A. It was specially planned so that you guys could get involved with all the experts and ask those questions that is coming in your mind. Because many times I feel lost in a talk, and when I hear my colleague ask a question, it always makes me think, oh, was that simple or was that so complex? So this is always a good sign. So Diksha, thank you for supporting this brand of conference organization where people give time to sort of take questions and also discuss, not just show something and then leave, right? So this is always you have supported that. So Diksha, welcome. Please say a few words for ACS.
Thank you, Jyotishman. It's truly an honor to be part of this scientific community and the discussion. And as you rightly mentioned, for last decade, sometimes it feels it's too long an association, but often, it keeps providing this varying flavor, how science is evolving and really seeing all of your collective passion. I joined 6:30 and I was really totally tuned into seeing you, Abhishek, Devashri, and Debu just could recognize from voice. Remember the time from Kaleidoscope. So it was really virtual replay, deja vu from the Kaleidoscope time. So really, really appreciate for giving us an opportunity, for making us part. And truly happy and grateful to support or be part of any meeting which brings high quality scientific discussion. And the range you covered into the discussion and the different topics, speakers, and everyone, I think that is best use everyone's time. We could really see if we can discuss science in a more free-flowing space without constraint and ask whatever comes to our mind. So these type of meetings are highly required. From ACS point of view, it's the first meeting for us in 2026. I wish I was there in person, but for different reason, I could not make it. But I'm so happy I could even join it virtually and listen or get some flavor of it. 2026 is a special for ACS. We complete or we will celebrate 150 year, which is an extraordinary milestone for an organization. And personally, professionally, both special. A lot of things will happen and different things will come through programs, efforts, and initiative. So this will be a very high festivity and celebration year for us to really celebrating science across the world. I don't have much to say, but I will be happy if there are any specific questions, but really congratulate and thank everyone who participated into this high quality scientific meeting.
Thank you. This was fantastic. I think we can get opinions. Really engaging for us. We have made sure we have extracted the entire juice from these two foreign gentlemen. They just arrived today in the morning. They have not batted an eyelid. They have listened with rapt attention and maybe a little bit, but I really am happy that we could hear them and we could all interact from the institute as well as from outside, interact with you, and this is all possible because ACS supported us so well. I just want to break away and sort of have this questionnaire, and this is something that we plan to do, and I think so maybe the associated editorial group is current editorials. Yeah, can I do the chair? Yes. So. Okay, so it's always so you can take breaks. You can see. Yeah, same. Yeah. So we.
Hi, Diksha.
Yeah. So and a quick sort of interaction session with the current editors and editorial board, people who are engaged with ACS publication. And I just wanted to start with sort of a set of questions for the editors, especially people who are managing the publication part. So I have like 3 questions that I would like to ask. One is, I would sort of go one by one. Maybe I'll start with Steve. And this is a general question that is coming up quite a bit across with the changing nature of science and publishing business, which is about AI, the use of AI in publishing. And Diksha gave a wonderful presentation maybe 6 months back when she was in TIFR about AI and how DCS manages. But that is from a publishing standpoint that Diksha gave. We would like to hear what the editors and the editorial board think about this new manifestation of science.
So I've not been on the editorial board for a year, and there's been a lot of change in the last year. I haven't had the benefit of appearing at the presentation either, but of course, there are concerns about this, but of course, it's a great tool. You can find out lots of wonderful things with AI. It gives you rapid access to a lot of new information. I guess the principal concern for editors is, are the authors actually writing the papers that are appearing in front of us, or are they being produced through AI? I don't know how much of a concern that is at the moment. If people are using it as a writing aid with real data and real analysis of data, I'm not sure I see that as a terrible and shocking problem. The concern becomes if the data is generated artificially. I don't know to what extent that's a problem, and to what extent that can be weeded out by editorial means, if you like, using AI to find that out. And of course, it's well established that people do fake images.
Yeah.
And there are tools which spot that. AI generated data, I don't know how that would be dealt with.
Yeah, Dave, you want
No,
to answer the discussion?
No, that's fine. Concern. I don't know how that can be dealt with. And I think we will need to have tools to check this, or you can simply ask to see the data. I mean, most journals now insist that the data is available. I don't know if that solves the problem. I guess you can make data which also has signal to noise or the junk that we do have to deal with in real data. So yeah, I don't know how to do that.
But I think there are some tools to check, and I think Diksha may have some comments on that. But let me first put Wayne, who wanted to join the discussion.
No, I was going to say that it's going to be interesting times, because in some form AI is plagiarism, right? So you're getting information that's not your content. So fundamentally, from an honesty perspective, it's a problem. The University of Toronto is totally caved on it, so they're allowing AI. So all you have to state you used it, and you have to state what your prompt questions were. Right. So then, are you going to be putting yourself forward of having used a tool and not really done the work? Right. So I think more fundamentally, the problem is going to be, and I don't know how to get around it, is one of the hallmarks of a scientist is their communication skills. Right. So how you communicate science, how you present something that others can understand it, that's going to disappear. There's going to be this massive melding. And so with people, I personally just think, I really appreciate. And Robert Hochstadt's in his prime. You were a paper. You heard him talking to. The style of writing, when you wrote into his papers, one could argue with the work and his interpretation. Robert Hochstadt. So I think we're going to lose some of the personality of science. So I don't know if there's any way around it, but that's my concern. One is the plagiarism aspect, and the other is it's basically letting people off the hook to develop communication skills.
Okay. Diksha, you want to add something to that?
I just keep thinking about ethics part. And AI and generative AI means very different thing to which stakeholder it is into the publishing ecosystem. There are clearly advantages when you see from publishing workflow, less human error, and a lot of other things. But when it comes from an author and researcher point of view, the ethical use of AI and understanding fully consequences is what we should really care about right now.
ACS is doing that, part of it, so.
So we use AI in some of the publication workflow where it is post-production workflow, but right now, or even like, finding the reviewers. So where let's say a handling editor has to find so many people for that, but all that decision making where the quality of decision, evaluating science or anything where you necessarily don't rely on machine right now because of the bias and things like that we are heavily, manual in that process. So at ACS, it's primarily the process optimization outside totally of the scientific evaluation of the content.
Yeah, Diksha, hi, Devu here. So, this is interesting talk. I don't think in this room we are going to solve any of it. It's good to discuss. Of course, each of us are going to have our opinion. It's going to form. It's not like 100% formed yet. The way, let's say, you have expressed, and I know for sure since I have been also involved with the publishing world, publishers are using AI. Now the ethical question therefore there is why the author will be questioned for using AI. Publishers are using. Why the ethics should be on author side only, why not on publisher side? If we are going to allow the publisher to use, I would say let's go and use it for authors also. Of course I understand it's going to happen. Yeah,
but I agree with this Robert Hochstrasser thing. It's like, I speak to my science. So if that, even if the blind review and all, even if my author name is not there, at some point of time, people should know, even if my name is not there on the paper, that this is from this group. I feel very strongly about that. So that actually comes from the way I write, the way I speak, and I think that individuality, if it goes away from science, it takes the away from it. I think.
That's my approach. But I feel AI is not going to take away the partners, and this is where perhaps AI huge, and then the personal touch, like author's personal touch, which you are saying, it's going to stay. Maybe AI is going to strengthen it. If you see a paper which is written by AI, you can read through and see through it. It's an AI written paper. But when let's say Ankara writes a paper, the style that is there, the craftsmanship, the artistic twist, I think AI can never replace that. That personal touch.
Hopefully,
I understood. But on the other hand, most of us like taking shortcuts. And when we start taking shortcuts, we actually don't many a times and forget how much we are losing in doing that. And that you can, I'm sure, see when you see homework starting, which are completely nonsensical. But
That's the classroom problem.
that has a parallel for here also. That needs to be somehow discussed so that it does not become
Teaching.
Yes.
Okay, Abhishek, you want to say something about this?
No, I'm not bothered about AI.
That's
Can I add something here? So this is exactly what Abhishek is saying. We should not bothered about AI. It's a smart assistant. We just need to figure out, does it have any value for me? Is it adding any value? Because in the end, whatever you are writing in paper, it's the responsibility someone need to own. Whether AI writes, your student write, you write, whoever write. It's the content that author will own. So this is totally up to the research group, what type of practices in learning or writing or communication they are going to use. Of course, there is a pitfall. If your students or anyone who does not know, let's say you have a raw experimental data, you put it up into AI and the paper is not published. So there are high chances that's like a public information. So people really need to know what part, where, how much, and all the publishers have that policy. Even at ACS publications, we have, clearly you need to declare, define, and several years ago, I remember there was a debate about the authorship, and a lot of the publisher who were like too soon into the process had to then come back and say, look, a machine cannot be an author. Obviously, there is that responsibility part. So more than who writes what, it's who own and is answerable to what is written there. This is more important.
Okay, I think we will move on from this because, listen, yes, Abhishek.
Wow. AI is not going to remain free. When AI becomes chargeable, users like us will not be able to afford it. So I'm absolutely not bothered about it.
Oh, I think there'll be a Popper's version.
It's not a very expensive food. It's a very expensive. So,
Well, science, maybe you have to pay a certain amount.
Yeah.
Okay, so coming from that last statement, I would like to ask editorial board and editor, I'll start with Abhishek here, as to what determines, in your eyes, a paper that is suitable for ACS catalysis, as opposed to a paper that has to be sent to even more specific journal. What is the thought process of an editor to decide that?
the first is the scope, which is clearly defined in the journal website. So the work done has to fit the scope that is being done. Second, the quality. The work has to be of high quality, by which we mean not just the writing quality, but the quality of data and different types of critical analysis of that data. And third, of course, is the relevance to the current audience. So whosoever reads the journal, they're a general set of people interested in large scale, large scope of the catalysis research is. Will this affect someone who is not directly working in that area? So someone reports some cobalt-based catalyst for water splitting. The fine it is, okay, if it's a great catalyst, it breaks all previous records, it deserves to be considered in the journal. If it's not a great catalyst, but there is some fundamental insight about the reaction that anybody working in this area in general would want to know, it belongs to the journal. But if it is 10%, 20% increment on what is already known and does not add anything new to understanding in that area, then it does not belong to a general journal catalyst. It should go to a specialized journal. So this is straightforward.
You find yourself as an author, these are maintained in other journals that you submit to?
In my experience. Well, this depends on the author.
Yes, it depends on the editor to make that call.
When you're young, most of your papers get rejected without doing. That's normal. Because you have to first earn the stripes. You need to establish yourself with the community in subject journal, so you're a credible scientist. Then when you send your papers off to big journals, people will take you serious. You have to earn your stripes, nothing doing. That's the brute, in my opinion, brute here.
Anybody wants to take a stab at it, anyone please?
I mean, what he's saying, that's saying it's largely absolutely what we see, not largely absolutely what we see. And which things are different, but it's not. I think each of us are going through or will be subjected to all of it. But other than that, how to choose a journal or which journal to choose versus whether it fits or not, and again, it would be very subjective decision, depends on the journal, which journal we are talking, let's say for SES, whether it is JAX, SES catalysis, inorganic chemistry, ORGLET, GOC, whatever other JFC. So I think it primarily comes down to the nature of the work and the novelty, which is definitely a debatable topic always and will remain. But at the same time, as we see, these goalposts keep on changing, okay? Which I guess Abhishek also alluded to. It depends who you are at points, it depends who you are, rather than which journal it is. And it's a summation of all that. I don't think just any work gets published without the novelty in a good journal, but at the same time having a name and fame adds.
True for every field.
Every field, yeah.
You want to add something?
I know you have gone through your.
It's also Steve King and the editors. I remember a day when there were only a few journals and it wasn't a big deal to decide which journal.
Yeah, that's right.
You would go to JCampus and you would get all the work you needed and you knew where to look. Right? And now, I don't know how many journals Nature has, Nature Communications, Nature Chemistry, Nature Physics, Nature Tomorrow, I don't know. It's what's going on in publishing, scientific publishing. I don't feel this diversity of journals is serving the community. And what I'm worried about now in my latter years, I was worried with bibliometrics, so you can not worry about AI, I'm worried about AI. Because I can bibliometrics coming in, and there was great concern that it was going to hand the reins over scientific evaluation, quality of work to where it was published. And because we all know there's a crapshoot when you start.
But it
Impact factor. So
but it actually did not do.
it sure is in certain places, you can't get a document, and publications and.
You can't get a faculty.
You can't get that wrong. And I can remember we attended some of the University of Toronto, we had one paper.
Yeah.
That would not happen today.
Today.
It was one paper, we all had to read it, and it was an outstanding paper. Einstein didn't get tenure today.
But you get a job.
Yeah, exactly. So James Macmillan, who just won the Nobel Prize, he finished his study, he was hired by Wisconsin without publishing a single day. So the thing is, it does happen, but it is rare now.
There's a.
I think now people feel empowered with it. I just wish it's a just.
Things are different. Now we have a much larger scientific
Well,
workforce.
that's.
That is happening.
Yeah.
See, you
That is-
say journals, Nature has 50 journals, DCS has 50 journals. It's because, I'm just saying,
Yeah.
like maybe 100. It's because the community demands it. Publishing houses, in my understanding, are providing what the authors want. Right now, if you look at the scientific workforce, ever since big population, highly populated countries like India, China, they have actually started doing.
That's true. That's
The
really.
numbers, the papers being something that have exponentially grown. Now we have to make space for that.
Yeah.
And the journal houses are doing exactly that. They're providing space for authors to come and publish. But
So I would like to hear a different opinion. Maybe Devashi has a different opinion on this.
That this multitude of journals is actually leading to any constructive thing in
That's-
science.
That's my.
Maybe because I want to publish somewhere, so I'm just finding the somewhere. But that's not serving science.
okay,
That's what I'm. But my feeling is the decision was made for monetary reasons. The nature family.
Yeah, so here,
That's all for.
let's hear the perspective from Diksha, because she is in the publishing business, so Diksha would know from the
I
perspective.
just find the nature rather.
Yeah.
Wrong, that's me.
Absolutely, it's absolutely phenomenal, right?
That's my feeling.
The charge is on me.
One last time, sorry, but the money, where does that come from? Our research budget.
Diksha,
See, we don't have a perfect system, but that's the system that still works. That's one thing I want to say. And the second thing, if you really see the number of articles submitted, even from India, that's growing every year within ACS in double digit. And even if you want more people to publish, there is very rigorous peer review system. And overall publication CAGR in the world moving into double digits. So clearly there are a lot of people who want to publish and they all need venue. However, publishers who are society publishers have more responsibility to provide appropriate platform, run more ethical practices around journals and impact factors and communities and the topic. So the way funding is happening, the way science is being served, the way research areas are evolving, it's important, we keep reinventing and reflecting how the journal scope should evolve. Even I have seen in last 10 years, a lot of journals within ACS, if you really, let's say, sustainable chemistry and engineering, right? And a lot of other applied journal. Those were not the journals even 10 years ago you had any research papers coming out of it. But now all these applied journals look applied material and interfaces growth. It has 6 and 7 applied family journals and clearly catering to a niche community. So this is more egg and chicken. You have more people aspiring to publish, but you can only publish certain number of papers. And so this is a very, I would say, sinking process. You need to provide more venues while maintaining some processes into place. So make sure a good science is going out.
Okay. Well, I think we will end there because I think these are topics that require, it's not going to be, there's no solution for this. These are ongoing things. We have to sort of make aware the younger community because we are now the senior community as faculty members, as publishers. So the younger community sees the impact of the impact factor numbers and number of papers. And everybody, I think everybody, students uniformly across, especially in physical chemistry and areas, and things take time, biology, things take time. So people do feel that there has to be some sort of a resolution or intrinsic hiring process need to be sort of rethought because number of papers and impact factor cannot dictate the scientific future or academic future of some bright guy. So this is something that I think we internally in our system we have to have more discussions so that we are more aware.
This is not a discussion with the publishing house.
Yes.
I still want to make a comment because somehow in my current role, I also do sit in some of the policy discussions as well. Look, impact factor is an endless debate. It was created a few decades ago for a purpose. And the way it is included into promotion, hiring, and career growth, and also more than an author or an institute, this is really that policy imperative, how much weightage we want to give onto that number. And it is easy when you have hundreds and thousands of applications, put up the number, some shortlisting and screening. So there need to be an alternative system that can justify not considering that. Second thing I want to say, earlier I was part of like a very big journal and then, doing the impact factor calculation. We can't compare impact factor across the segments. It totally depends on how many people are working. If you are working in a very narrow niche area, your impact factors are going to small. So there need to be a lot more awareness about the impact factor and its collective responsibility to educate people what impact factor mean. It's not an absolute figure we determine, a paper published in a high impact factor journal must be good or vice versa. So to me, it's more policy thing and administrator into the country really need to think about. If it will continue to be incentivized, people will continue to commercialize.
Okay. I just want to take a young faculty's opinion on this. Somebody there knows his faculties and he had very strong opinions on these publication journals and publishing the way you should think of. Someone would like to hear what you think while you are submitting a paper.
Oh, yeah, that is strong opinion.
Big deal.
Well, what was the question?
The question is, do you care about the impact factor while publishing your work?
No, here never goes very high impact factor journals. That's great.
Would you care about it?
No,
Okay.
because high impact factor journals don't care about theory.
I think that comes our own doing, yes.
Right. Okay. Well, I think I will end the session here because I think everybody is tired. There was a long, intense symposium, Diksha. We had 10 minutes of questions for every talk, and there was very detailed discussion. Everybody's talk became even more clear in the question answer session. So the purpose was served. And thank you, Diksha, for joining us for this short segment. I now invite Shomna to conclude and give the final remarks.
So now we are
Thank
going
you,
to-
everyone. It was really nice to see you all and see you soon in person somewhere.
Thank you. Thank you, Diksha. Okay. So I think Shomna has. I want to know.
Yes, if you are
Okay, guys, let's conclude it.
Okay, so I think we are all tired and ready to go home and have some food. Thank you so much for staying back till the end. So really, thank you so much, all the speakers, for being here with us today, and special thanks to you guys because your flight landed this morning and you had probably slept 2 hours in the last 30 years. That's what I heard. So thank you for putting up with us, and thanks to Abhishek, Debashree and Debuda for coming here and share your research with us. So starting with ultra fast electron diffraction, ultra fast proton transfer reaction using vibrational spectroscopy and transient absorption spectroscopy, and we had very nice discussion about using enzyme, how to do organic synthesis as well as think about inorganic chemistry and synthesizing metal, heme complexes. And very nice theory, singlet fission theory.
It gets deep to the warren.
Yeah, so yeah, it was very good. I really enjoyed. I hope you also had a good time here. But all of this was possible with very various different kinds of support that we have received from the department, our departmental administrative support, canteen support from the canteen, as well as support from the technical and audiovisual support team, support from the photography section. They is still doing the work. Support from department in terms of various other logistics, as well as of course JE for approving both Steve and Dwayne to come here and join us inside the TIFR. So and of course ACS for the sponsorship, and thank you all for staying up until the end. So thank you.
For dinner now. And we will just take everybody out and we have to take the back. We are singing.
Oh, yeah. Let's just say also, yes, on behalf of the Senate. So really appreciate you guys. The really interesting.